the war was over and the boys were all coming back from the war with their demob suits and their bowler hats, the secretary of the RSGB wanted to get the London lectures going again, and he came to me and asked me if I could give him a show, and I said, yes, I'll do something for you. What would you like? Well, I was supposed to know something about aerials in those days, and so I said, well, I'll do something on aerials for you. He said, right-ho, and so I went away and I talked it over with my friends at EMI where I worked, and one of them put up a suggestion that I should make some little scale models of real aerials and make them all work on microwaves on 3000 megacycles. And so we scrounged round the remains of our work on radar during the war, and we found a klystron and rigged up some gear and took it up to the IE at the lecture night, and when I got there I was surprised to find we had 250 people with standing room only in the main hall of the IEE, and so I proceeded with the lecture, and it went very well. Everybody seemed to enjoy it very much. I went home, and it wasn't very long before somebody else came up and asked me if I could do it, and it went on ever since. They've never stopped asking for it, so I suppose there must have been some virtue in the thing. Anyway, we went on for about 3 lectures, and then everything blew up, and I had to give a flat lecture without any sound, but we then set to and made some reliable gear, and that's been working ever since. Now, the gear itself comprises a klystron working at 3000 megs and a metal deck with a socket in the middle into which I can plug the little wire models, and also some auxiliary cables I can plug in to put models up in the air away from the deck. And I have a little magic wand with a detector in it which I wave around in front of the aerials, and you then see you then hear the output of the aerial on the loudspeaker, and you'll very soon find that you get a 3-dimensional impression of what the radiation pattern of the aerial really is.
Gentlemen, I give you Mr. Dud Charman, G6CJ. And Dud, a very good evening to you. Excellent. Excellent, gentlemen.
Well, good evening, everybody. You've heard roughly what it's all about, and I'll just explain a few things about what I've got here for the benefit of those of you who haven't seen it before. Incidentally, put up your hands those who've seen it before. Well, you can go home for a start, it hasn't changed. Now, I'm going to show you how aerials radiate and how the aerials are put together to give the various directional patterns and so on that you require. I'm doing this by means of scale models. Now, scale modeling is perfectly legitimate as long as you have good conductors and good dielectrics. You just scale the frequency inversely with the wavelength, and the model behaves just the same as the full-size one. Now, my models are working on 3,200 megacycles, and that makes the half wavelength about 2 inches long. That is a half-wave dipole at 3,200 megacycles. It's made of 20-gauge wire, and it has about a 200-ohm line. I think it's something like that. That's convenient for getting out of my cable. If I have low impedance aerials, it suits them. If I have high impedance ones, I make the thing 3/4 wave long, and it steps them up to, say, about 600 ohms. Now, the generator is down here, and It's a Klystron of the type which you're probably familiar. And I have various cables, one coming up to this stand, and I have a socket in the middle of this copper deck. Now this copper deck, say on 14 megacycles against my models, represents about 50 acres of nice, good conducting soil. And it will give you very good patterns. It gives you textbook patterns, much better than you get in real life. But anyway, that's the best I can do. It's rather difficult to scale model bad conducting surfaces at these frequencies. Now, I have a little magic wand here, which will pick up the signals radiated from the aerials, and by waving the wand around, you can very soon appreciate the radiation patterns of the aerials as real solid diagrams and not like the flat pictures you see in books. The first thing we consider is the wave that leaves the aerial. If I hold my detector parallel to the aerial, I receive a signal. If I turn it at right angles, the signal goes out. Now that's the first thing. You see, the wave is polarized. The electric field of the aerial lies along the wire, and I have to lay my wire so that the electric field can intercept it. If I turn it at right angles, of course I get no volts along it, but if I've got some volts along it, it picks the signal up. Now this wave in free space goes off to infinity and disappears into the distance and never comes back again, and that is called a travelling wave. Of course, we don't have travelling waves in real life. There's always reflections about, and when you have reflections, you get standing waves. If I put a sheet of metal up here, you'll see there's a standing wave pattern there. The wave hits the copper. The electric field induces a current in the copper. That in turn re-radiates, sends a wave back in the opposite direction. The forward and the backward waves interfere and give you the familiar standing wave pattern. And in real life, we always get that mixture to some extent, the free space travelling wave and the standing wave, because we always have obstructions around us. Now, the biggest obstruction, of course, is the Earth itself. And I'm going to show you, by means of a model, how we work out the effect of the Earth. The dipole by itself has a uniform pattern all round it. That's because the electric field lies in that direction, and the field is symmetrical about the wire as an axis. If I go across the front of it, you see the signal comes and goes. Now, the way it works out is this. This is how we arrive at the patterns. There's the dipole, and there's a voltage along the dipole representing the electric field of the aerial. If I look at the dipole from straight on, I see the full voltage. If I look at it from down here, I see a foreshortened version of the aerial. The aerial now looks shorter. And so I get a correspondingly reduced voltage. If I go right down to the end, I just see a dot and no voltage at all. And if you follow that round, you arrive at the pattern of the aerial, which is like that. And of course it's on that side as well. But you've already seen that it is in fact a sort of donut. I go over the top, but every time I come to the end, there's a null. Now I'm going to show you how we work out the effect of the Earth by means of a special model. This dipole, this aerial has two dipoles on it on a straight piece of feeder, and they're separated by half a wavelength. This means that the two dipoles will be in opposite phase, and therefore in broadside to it, you will get no signal. The energy going by that path or by that path takes the same time, so the waves will be in phase going up. And if I consider the path off the first aerial and the path off the second one, because that's a half wave, it does an extra wavelength of travel, and again they're in phase. So this aerial will give you a broadside pattern, rather like it will give you the dipole pattern in both directions. There's now a null in the front where the two opposite phases cancel. You see, I've made two donuts of this aerial, two spheres in fact. Now, if we have the null plane in the middle, and we put a sheet of metal there, and nothing happens. The pattern doesn't alter. See, it's the same with or without it. So we can represent this as the ground itself. And consider that the second dipole, the lower dipole, is an image of the one at the top. If we consider that to be the ground, and I'm looking at the end of the aerial. Now we're getting two waves from it. They're in opposite polarity. And if we take a wave which goes off like that, or like that, we'll go a long way so as to a parallel, and this wave is exactly the same as if it came from there. Because when the wave enters the conducting surface, there's an entrance phi of 90 degrees phase angle, and there's an exit phi of another 90 degrees phase angle, so that the phase comes out in reverse. You have to allow for that, but of course that is why there is no signal in that direction, no signal along the deck. If we follow this round and allow for the extra path that wave has gone, and therefore the relative phase of those two, and plot it, we come to the pattern I've just shown you, which is like that, looking at the end of the aerial. And this is how it can be done. You can always reckon out why the image is in antiphase, because if you draw the electric field, it's got to come down to Earth, and if it's going to go to the image, the lines of force have got to go between opposite charges, so that must be in opposite phase. On the other hand, if I stick my aerial vertical, there's a vertical aerial standing above ground, we'll mark its polarity and put an image here. Now we draw the lines of force, and they come like this. You see, positive goes to negative and negative goes to positive. They're in phase now. This makes the fundamental difference between the horizontal aerial and the vertical aerial. The vertical aerial sends out an electric field which is lying along the deck, and that's the situation it likes. It likes to have its feet on the conductor. The horizontal aerial can't send an electric field along the conducting deck because the conductor short circuits the electric field. Simple as that. Well, now having done that, we'll transfer to the Earth plane. and put in the corresponding aerial, which is, it's a half-wave dipole. It's going to be a quarter wave above the surface. In order to get the half-wave length of feeder in, you see I have folded the feeder around. I always use half-wave length feeder for these centre-fed aerials. Now, here is the top half of the pattern I showed you a few minutes ago. You see, it's a nice sphere sitting above the deck. Well, that's all right. The aerial's radiating. Of course, it's more powerful in effect because we've now got the power of the image in the upper radiating part. But if you want to work long distances around the Earth, if you want to work on the HF, if you want to work the HF bands and work DX, it's not much good having an aerial which sends all its energy straight into the sky. Here's the Earth. The waves are conducted round it by reflection from the ionosphere, which I've drawn simple, but of course it's several layers. We'll transmit from here and we'll receive over here. Now, an aerial which sends vertically isn't going to get there. My pattern was like that. There's very little aerial radiation going there, which is where it's got to go to reach that point down there. In other words, it's got to go along the surface as near as you can get it. Well, the old age rule is to raise the height of the aerial, so it will go up to a half wavelength high. The aerial is a half wave above the deck. As I said, no radiation along the deck. There's no radiation in the sky either, because the image is a wavelength away, and so it cancels the radiation from this in the vertical direction. The radiation comes out over here. The angle is actually 30 degrees, which is very easily worked out by referring to that diagram. Okay, well, now we'll raise the aerial a bit more. I'll take it up to 3/4 wavelength. It's a folded dipole just to give a little variety to help my impedance arrangements. And at 3/4 wave we again have signal in the sky. And a main lobe down there as well. So the aerial now has sky wave and a second lobe. The lobe is at about 22 or 23 degrees, and we're getting on, getting the wave down towards the horizon. Now I'm going to a wavelength high. And again, there's no sky wave because the image and radiator are out of phase. The lobe which was on the top at 3/4 wave has now moved over. And the two lobes are at 20 degrees and 60 degrees. And if I go on increasing, every time I go another quarter wave, a fresh lobe appears, and in the next quarter wave it will turn over, and if we go on, we'll have a bunch of bananas for a pattern. Now, that's fairly good. See, if I'm getting 20 degrees, I might try and draw 20. I won't quite get there with 20 degrees, maybe, but we've got 3,000 or 4,000 miles without any trouble. It wants to be about 15 degrees to get there. I got there by 2 plows now. But of course that second lobe in the pattern, which I showed you, the second lobe in the pattern, 20 degrees and 60 degrees, is a bit of a nuisance because both waves will get to the other end, but one of them will do a lot more travelling than the other one. It'll go by many more hops, and the two waves will not necessarily arrive in phase. In fact, it's worse than that because the ionosphere, being a natural phenomenon, acts according to Lenz's law, which says nature invariably works to the disadvantage of the experimenter. And it's an unstable medium. It's on the move all the time. Now, I can't show you very well. I can't scale the ionosphere, but you see, if this layer moves around a little bit, we get fading of the signal. And of course, on my scale model, I have to move it a long way because there are only a few wavelengths. But if you say between here and New York there's 10,000 wavelengths, then it doesn't need much change in the two paths to give you a maximum or a minimum. And the small movement going on all the time produces the fading. So what we've got to do is to get rid of this upper lobe. And the way this is done is to avoid having aerials with spaces more than about half a wavelength long in them. You fill in with extra dipoles wherever you can. You don't go more than about half a wavelength. 5/8 is the maximum before you put some more dipoles in, and then you destroy all the extra lobes. Now this model is the same as the one I showed you for the image, but if you look carefully you will see I have crossed the feeders. I've twisted its neck so that the two aerials are now in phase, and this aerial is going to push the signals forward. The lobe at 60 degrees has practically disappeared. It's rather slightly mixed up with the other one, but you see it's very much weaker. Now, nearly all the power of the radiation is in the 20-degree lobe, and that, of course, is the way it's done. If you do it in style, of course, you have a lot more elements. This sort of thing, for example. This was a nice aerial we had on 2 meters in the days when we used to make arrays. These are half waves, and we adjusted the thing so that the end impedance is all added up and gave the right impedance at the feeding point. So that's how the height affects the patterns. Now let's consider the length of the wire. We've been working with half-wave dipoles so far. I'm now going to take an aerial which is a wavelength long, what we call a full wave. It's fed in the center, half-wave either side. And you'll see that it's very much like the dipole, but a little bit sharper. Put the dipole in for comparison. I don't know whether you'll notice this, it's only about a dB difference.
Just do the other one again.
Yes, I will.
You've got the hum again there,
All right, my fault. Now that's a little broader than the dipole. I don't know whether you'll notice it. It's not very much difference, but there's the dipole. So you've got a little bit of gain. But there's another important thing. I'm feeding this aerial in the center. Now I have the same aerial and I'm feeding it at one end. And we'll see what happens when we do this. For those of you who can't see it, the aerial is lying at an angle. Most of my aerials are lying at an angle because the socket's crooked. Now you see that aerial has split lobes to it. and you see the pictures of them in the book. But what I want you to appreciate is that this lobe coming out here in this direction is really a collar sitting around the aerial. It's there, it's there, it's there. It's a little bit weaker at the top because the aerial doesn't want to radiate upwards. It's the wrong height to do it. So you see, by changing the feed point, we've altered the pattern of the aerial. Now this will always happen when you've got an even number of half waves in the system. If you take an odd number of half waves, it won't happen. The pattern will be the same. This is just a matter of how the currents are distributed on the aerial. I'm now going to take a very long one. I think this one has got 6 half wavelengths in it. Measure it with my half wave ruler. Yes, it's 6 half wavelengths. Now, the 3 half wavelength aerial should give you 3 lobes. And they're going to be in phase. So, although we've got 6 half wavelengths, we only get 3 lobes. 1, 2, 3. And again, of course, they are like this around the end of the aerial. I shall use that model again presently. Now, before we leave the HF bands and go on to something which is more suited for VHF, I'll just consider the vertical aerial for a moment. As I said, the vertical aerial likes to, the electric field likes to hang its feet on the conductor, so the radiation goes along the deck. And looking at the sky, we're looking at the end of the aerial, and there's no signal at all. And of course, it's symmetrical, and it's got some gain over a free space dipole, about a couple of dBs. So it's a very attractive aerial if you want to get low angle radiation and work DX. It doesn't work too well if you live in the middle of a city, because it's rather difficult to define what is the Earth's surface in that case, and you've really got to get it way above obstructions to make it work. If you live in the country, it's a very, very good aerial, and if you get up on the roof in the city, it'll be a good aerial too. From a propagation point of view, it's not always better than the horizontal aerial. This is because the waves aren't always coming in at the angle to suit it. Now, I've talked to you a little bit about directive arrays for HF bands and how to get the wave down to the ground so that it goes the long distances properly. But back in the 20s, when the amateurs were busy releasing the short waves, the commercial people were very interested, and they were doing a lot of work to see if they could use the short waves, and they realized, of course, that they could use directive arrays. The theory and principles were understood, and they could even fit them with reflectors, and they knew that if they did that, of course, they could get a much better signal by focusing all the energy in the right direction. But they had to build very large arrays to do it properly, to get, say, 20 or 30 dBs gain. They might have 4 dozen dipoles, and each one with a reflector system behind it. And this is a very big aerial. It used to hang up on 300-foot towers, and it was worse than that, because when they really started trying to use these aerials for point-to-point communication, they found that they had to change their frequency from time to time during the day because of the way propagation was changing. And this meant that they had to have different arrays because these arrays were tuned arrays. So you see, it all became rather expensive. They might have to have half a dozen great beam arrays down at Dorchester just to run the London to New York circuit. And when you consider that one of these aerials with its 300-foot towers and triatics and all this knitting hanging down from it cost about as much as a building estate. And so there was great activity to try and find a cheaper way of doing it. And the RCA in America were looking at the properties of long wire aerials. And they thought perhaps if we did this, if we took two long wire aerials, many wavelengths long with pattern like that, and put two of them up so that the main lobes were both pointing the same way, they would add up, and all these others wouldn't be cooperating because they weren't pointing in the same directions. They weren't coherent. And this turned out to be the case. We can easily show you how it works because I'll take an aerial which has got 3 half wavelengths in a side, and that's its pattern as a flat aerial. Now I'll turn it round. Immediately you see you have a directive gain, and if you make the aerial perhaps 5 or 10 wavelengths long, you get quite a lot of gain. But of course this is still a tuned aerial. It's got standing waves on it because the ends are free, and they knew that if they could put the right terminating resistance on there to catch the wave that went forward, catch what was left of the wave coming forward so that nothing went backwards to send a beam that way, then the thing would not only be unidirectional, but it would also be a broadband aerial. They could take it over a wide range of wavelengths. Well, they didn't succeed. They tried various things like long bits of cable with insulators and resistors in series and so on. But these were only empirical things. They didn't really succeed. But the people at the Bell Labs said, well, really, it's very easy. All you do is to back another one on. And then you've got your terminating resistance up in the air. You see, you couldn't put a terminating resistance on there and then take 100 feet of wire down to the ground because that isn't terminating. That's part of the radiating system. So the Bell Labs obliged by bringing the terminals of the aerial together. Now you have the rhombic aerial. I have here a rhombic. So I will put on for you. Have to have some masts to hold it up. It's a rather difficult model because it's not really transportable. It doesn't keep its shape. The feeder gets bent up in knots. Anyway, there it is. The terminating resistance, of course, has to match the characteristic impedance of the aerial system itself. At 3,000 megacycles, it doesn't seem to matter very much what you hang on the end. The resistance at 3,000 megacycles has no connection with the colours printed on the resistor. So you just go into your box of miniature resistors and find one that works fairly well. Now you'll soon see that we have here a powerful aerial. Quite a sharp beam. And that's what you get with 2.5 wavelengths a side in each leg. And you see it doesn't really radiate anything much anywhere else. The termination is letting a little bit to the rear. But you see, all the other lobes of the aerial have got lost. And all the energy comes out here. And a very nice aerial it was, and it's lasted from the early 30s until this day, until somebody invented something even better. Now I'm now going to talk about reflectors. That's a vertical aerial, and it will be convenient for doing our reflection experiments. If I put a sheet of metal in front of the aerial, of course it stops the signal entirely. If I put it behind, there will be points where it throws the wave forward and points where it splits it somewhere else. Just the same as when I showed you how the Earth screen worked. You see there are many points where the phases are right for it to go forward. What happens when at one of these zero places? There's a zero there, you see. Well, the wave's got to go somewhere. It's actually split and gone out either way. Now I'll go to a maximum. You see the beam is then forward. Well, of course, even if you want to work on VHF, you can't have a sheet of metal the size of a football field standing up the end of your garden. You can't even do this. You can do this on VHF. And here's a typical VHF reflector. Isn't working very well today. It cuts out a great deal of the signal. And when I tell you that the mesh is 1/8 of a wavelength, and I haven't bothered to solder the wires where they cross, you'll see that it's doing quite a lot of work. I'll show you now the difference between front and back. Anyway, stopping the wave. That's the forward wave. There's the backward wave. It's doing about 20 dBs. So if you're on VHF and you want to put up a aerial on 2 meters, you don't have to have a large sheet of gold-plated copper to make a good reflector. You can use a piece of chicken wire with about 3-inch mesh on it. It'll work nearly as well. Of course, the Americans did do this football field on its side out in the Arctic, in the dew line. They built some reflectors up there for their job up there, which were that size. Now, at most wavelengths, of course, even this is a bit too much, so we have to be content with a piece of wire. Let me introduce to you the parasitic reflector. As you see, it cuts down the wave at the rear, amplifies it at the front. You'll notice, though, that the effect didn't go so far back as when I was using this. When I was using this, I go a long way away because, of course, this was picking up a lot more energy. This picks up very little. Well, now, But about the time the rhombic was being invented, the hams were beginning to think about aerials with reflecting systems. And nobody knew much about the practice, and so W8JK in Ohio State University was very busy experimenting with parasitic reflectors. Here is an aerial with a parasitic reflector. The long side is the reflector. The aerial is looking that way. You see it has quite a good back-to-front ratio, and that could be improved by trimming it. Now, what was found was that the back-to-front ratio improved as you close down the spacing. As you close down the spacing, you have to adjust the length of the wire, because in theory you want two aerials a quarter wave apart, and that one 90 degrees ahead of that one. And then the wave will go in that direction. In other words, they're phased so that the wave leaving that wire comes in step with the wave leaving that wire. And the wave going the other way gets out of step. That's solid, and that's a null. Now, you can't do it by feeding you can't do it easily by feeding those two aerials. You've got to produce equal currents in them. And the aerials, in fact, have different impedances when they're coupled like this, and it all becomes very difficult because you have a quarter wave of feeder between them, and you go on messing about for a long time. It was found very much easier to use the parasitic conductors, but then the problem was they were too far apart at a quarter wave. There wasn't enough energy coupled into this one to do the reflecting properly. And so they had to close the spacing to get more power into it. Now, of course, we haven't got this back-to-front business working properly. So you've got to make the wave slow up in here, and that is done by making this inductive and giving a bit of lag, which makes up for the bit of the quarter wave you've taken away. You've put an inductance in the middle. Actually, in practice, it's easier to just cut the aerial a little bit longer. That's how it's done. Now, having done that, they then proceeded to find that as they closed up the spacing, the back-to-front ratio improved, and the radiation resistance disappeared with high velocity, so that you finished up with a very, very sharply adjusted aerial with a very, very narrow bandwidth. Well, of course, they had to come to a compromise, and they settled the compromise at about 1/8 to a quarter wave, and that's what we use today. Now, you can imagine, if you like, that this area is cut a little bit long, and it blows the wave forward. The question is then asked, suppose we cut an aerial short so that it's not inductive but capacitive. The phase will now be advanced. Will it suck the wave forward? And the answer is yes. There's a blower, there's a sucker. And so Krauss investigated the directors, as they were called, and he found really that there wasn't anything in it. The results were just about the same whether you use one or the other. But of course it wasn't long before somebody said, well, can't we have an aerial with both the suck and the blow? And so arrived the 3-element array. You see how easy these models are to make. You just get some wire and a bit of polystyrene and a soldering iron and push them together. Now when I put this in, you will very soon realise why it is that aerials of this type are on the roof of every house in the country. Here is the forward beam of the aerial. It's quite clean. We've measured that little side lobe at the back, and it's minus 20 dBs. Compared with the forward, there's nothing there. Now, this was called a Yagi because Yagi invented the director. He did it about 1928 at Tokyo University. He didn't actually produce an aerial like that. He wrote a paper in which he had many arrays of aerials, of radiators and reflectors and directors, and he invented a thing called the wave duct. But he didn't actually produce that particular design. So, but anyway, it's been given his name to record the fact. Now, what Yagi did include in his paper was a thing called the wave director, which was what I call a board of directors. You increase the length of the aerial, in effect. You see, it gives you another 3 or 4 dBs. Gives you quite a bit of gain. It does more than that. You can get the wave round the corner. I'll turn it towards myself. It's gone from over here now. You send it into the sky. There you are. You can get it round for about 45 degrees before it loses grip. Well, anyway, you can have that one for nothing. You put that in the middle of your garden, and you stick one of those pointing to South Africa, another one pointing at the States, another one pointing at BK. You see, just turn the 3-element aerial down in the middle. Now, that aerial looks pretty good. Part of its virtue is due to the fact that it is at the right height above the ground. And to show you what I mean, and don't be alarmed because it isn't like this in real life. The Earth isn't so good as it's supposed to be. But you see, this aerial's at the wrong height. And it split its beam. Now, I can show you that there's no cheating going on because I'll just reduce it to the right height. It now has the standard pattern. But, of course, it isn't quite as bad as that in real life because I've got a very good earth plane to work on. And on the VHF, of course, you have the aerial so high it's a long way from the ground, and these effects are not quite so important. I'm now going to introduce you to the slot aerial. It works on a principle discovered by the opticians in the last century. They said that if you take a large sheet of metal like this blackboard and you cut out of it a strip, and you take it a long way away and put it over here, then that piece you took away is the dual of the hole that you left. And it was done for light waves, but as they are electromagnetic waves, it works for our waves as well. And it amounts to this, that if you chop that in half and make it into a dipole, and do the corresponding thing here, which you can't put a series connection, you have to put a parallel one. Bring the feeders down there. You have two aerials which are duals of each other. The duality is like this. The electric field is horizontal in that aerial, it's vertical in that one. The magnetic field is that way in this aerial, it's that way in the other aerial. And everything is the duality. But the patterns are the same except that the electric and magnetic fields are interchanged. So this gives a pattern with a field like that of a dipole, but with the magnetic and electric fields interchanged. And so this aerial should radiate uniformly in the E plane, the plane of the electric field, would have the dipole pattern in the magnetic plane. I have a model here. Here it is. It's one wavelength around the perimeter of the slot. In other words, it's a half-wave slot, and it's connected to some open wire feeders across the center of the slot. Now you'll see that although the slot is vertical, the radiation is horizontally polarized. And my aerial is actually giving a spherical pattern. It's actually giving a spherical pattern. That's because it's not an infinite sheet of metal, it's a finite sheet of metal. And it should radiate uniformly all round the aerial in the electric field plane. The fact is that I've cut the metal down till it's only half a wavelength wide, so that the current in that side of the slot of the strip interferes with the current in that side and cancels the radiation going out sideways. Now, that has already given us a little bit of gain. It's turned this in from a dipole pattern to a spherical pattern, so it must have 2 or 3 dB of gain. And one immediately asks the question, well, how long can we go on reducing the metal and still have a slot aerial? And the answer is that you can take all the metal away and just leave the slot. Of course, you have to have a piece of wire to show you where the slot was. And so you have what has come to be known as the skeleton slot. And here is the skeleton slot. See, it's got that spherical pattern. And of course, as you know, it developed into this kind of thing. The hams used plenty of them. The Argy arrays with slot feeds to them. It also comes up in another form known as the quad. You see the pattern of this thing on its own is very much the same as the pattern of that. That's due to the deck. Don't worry about that. See, it's a spherical pattern. If you put it above the earth plane, it will behave rather like the Argy. And I won't be drawn into the argument about which is better, because nobody really knows. I certainly don't. Now, we have to close. I could show you a lot more. You've only seen half what's in the box, but we've got to close. And so I'm now going to put on what I call the set piece. This final exhibition concerns the circularly polarized wave and the circularly polarized aerial. Now, I expect some of you have difficulty in thinking about circularly polarized waves, but I'm going to represent it to you as a spinning wave. You put some energy in at the far end, and the wave travels along the wire, and the pitch and the diameter are adjusted so that it doesn't matter whether the wave leaves the wire there or whether it leaves it there. Everything coming out is all in the same phase. And you can imagine that the wave screws itself down the wire and screws itself away through space. And you can imagine it as a spinning aerial. And I think the correct way to talk about it is to talk about a right-handed circularly polarized wave when you've got a right-handed screw thread. If it isn't, it should be. Now you will see that it is circularly polarized. Remember what I said about looking at the wire, and if you can see some wire, you can see some field. Well, you look at this wire, and which way is the field? You see the wire in all directions, so the field is in all directions. On the other hand, if I come around the side and look at it from this aspect, the average position of the wire is vertical, and I get vertically polarized waves, but no horizontal. So it's not circular around here. In the intermediate position, it's elliptically polarized. Now, The mathematical way of looking at the circularly polarized wave is to regard it as two waves. One like that, a quarter wave apart, and as you see there, a quarter wave difference in electric and magnetic field positions. And you imagine that as the wave comes forward, it spins round in that position, so you can see it's a screwing wave. But you see there we have two component plane waves making the circularly polarized wave, and my probe at the moment is only receiving one of them. If I want to receive all the power, I must use a similarly circularly polarized receiving aerial. And now, of course, you see the aerial has some gain. It's extended in space, and therefore it has gain. Therefore it has a pattern. It's not a bad pattern. Of course, they've got about 6 turns on it. It's nearly as good as a Yagi. But there is another factor about it. You must have the thread the right way round. The wave is, this aerial is left-handed thread, and it must screw itself into this left-handed thread, otherwise it won't do any business. To show you what I mean, I'll put an opposite-handed aerial on the transmitter. Oh, sorry. If I put my left-handed aerial on it, you see, it doesn't do any business. Mind you, you know that if you I have a piece of mirror here. You know that if you put a left-handed screw in front of the mirror, it turns itself into a right-handed screw. And this reflects light waves, which are electromagnetic, so it reflects our waves.